This is my Lab 5 magnetic braking with Faraday. The system was the magnet and the foil, the surroundings with everything else, the room, the earth. The initial conditions are assumed to be room temperature, standard atmospheric pressure. The procedure was to have a tube of aluminum foil with known measured values of like height and width held vertically. The magnet with the known magnetic dipole moment from Lab 3 was dropped into the tube, and the time it took to fall was calculated using the start and end timestamps in a slow motion video. The purpose of this lab was to explore the interaction between a magnet and an aluminum foil tube that's not magnetic, basically electromagnetic induction, and making a computational model to resemble it. The main principles are Faraday's law, gravity, and the magnetic forces and induction. And some of the results previewed is the falling magnet will experience a noticeable reduction in velocity from the induced to the force from the induced tube's current around the magnet, and that works to stop the magnet's motion. This is the code. The initial conditions are set on the top right, the length, width, the mass, and magnetic moment. The magnetic field is made at the top left, setting up that just like a normal equation. The magnetic flux is then made below that using those setup equations based on the variables we knew. And then the B fields for each ring were made. And the final step was just pulling all that together to make the force from the magnet in the y direction, and Fnet was just adding that and the magnetic and the gravitational force that we already calculated. And below that was calculating the bar's velocity and the bar's position based on those forces and velocities. The results was very close to what we measured, just like a couple hundredths of a second off. And this is what it looked like at certain times, with the magnet following the north and south ends, the velocity graph on the left, and the time in seconds on the right. The actual results, the average time was 1.586. Calculated that the computational results was 1.594, so it was really close, which is interesting. But yeah, we just took all the start times, added them together and averaged them, all the end times, added them together and averaged them, found the average time based on that, and then also did the other way to double check. What if the resistivity of the conductor was reduced as basically to zero? How would the dynamics of the falling magnet change? Less resistivity would lead to a higher induced current in the tube, which would mean that it has more force and slow the fall more. If it could be perfect, the magnet would hypothetically levitate. And then what if there are holes or slots cut into the tube? How would this affect the ring currents in your model? The holes and breaks would cause the same in the current, which would weaken it and make it a lot more difficult to code properly because the induced current would not be continuous and the fall would be faster. The possible sources in error would be in the measuring time used in the videos and not starting at the same spot or velocity for the fall. The purpose was fulfilled for this lab as we created a computational model successfully using the observational data and matching it. So the model worked and the calculations were made properly. So induction was observed. Yeah, thank you.